So in this chapter, we're going to learn some basic, of Schrodinger equations. But before that, we actually need to prepare us. So we're going to start from those, basic foundations of waves, by mostly talking about this Fourier transform. Okay. Some of you may are familiar, some of you may not. Okay, so we're going to review a little bit properties of Fourier transform. Okay, and this one actually is related to the superposition principle in quantum mechanics. Okay, right. So we're going to know how to do this. Sorry, and then we're going to discuss the meaning of the quantum waves, right? So basically, to understand this Born's interpretation, right? And that's related, of course, to quantum measurement. So the key things in this quantum measurement is to try to calculate the expectation values.
Sorry, Professor Liu, we cannot see your writing.
Okay, so let me escape this sharing first, and then I don't know what's happening in this. I see. Okay, now can you see right now? Can you see the white button right now at this moment?
No.
Do you see?
Yes.
Okay. Okay, so we had some. So now for the basics of wave functions. So we're going to discuss the Fourier transform. Okay. And this is related to the superposition of waves of states in quantum mechanics. Okay. So that's why this is important. Okay. And then we're going to discuss this Born's interpretation of the quantum waves. Right, so that's basically the probabilities, right? So it's called a probability amplitude. Okay, and from that we can discuss, for example, the expectation values of physical quantity. And we know that in quantum mechanics, the important thing is that you cannot measure a pair of quantities arbitrarily precisely. So there's something called a variance. Right, we're going to show how can we calculate variance if we know the wave function, if we know the the states, okay? All right, so that's the second part. And then, of course, the third part is the core of this course. That's a Schrodinger equation, okay? Schrodinger equation, and then we discuss this time-dependent Schrodinger equation, okay? And time-independent Schrodinger equation, okay? Right, so in this case, you have the time dependence. In this case, we can separate the variable so that you have no time dependence in this one, okay? So you have this one. So we're going to discuss eigenstates, so eigenfunctions, and eigenvalues. Okay, and how to form the evolution, okay, from this eigenfunctions and eigenstates. Sorry, eigenfunctions and eigenvalues. So you have of course you're not required to understand this meaning at this point. But that's the one-page summary of what we're going to learn in this lecture, in this chapter, okay? All right, so let's start from the beginning, the waves. And we can take the example. It's the EM waves. But EM waves is just too complicated, okay? We know that EM waves has two components, have an electric field, right? So that propagate in a space-time. Okay, and this is just too complicated. You need 6 components, and to understand this one. So you have 6 components or 2 vectors in 3 + 1, 3 spatial dimension and 1 time dimension, space-time, right? It's quite complicated, so we want to, for all purposes, want to simplify this one a little bit. Okay, for simplification, first of all, you know that the electric field and the magnetic field, they are actually related to each other. If you know electric field, then you also know the magnetic field and vice versa. So we only need to keep one of this one, for example, electric field. This is the one thing, right? And secondly, we know that this E actually can has 2 polarizations, right? So we don't need to consider too many of them. Just let's say, just take one. Okay. So that means we only need to take one polarization. And thirdly, let's just consider a wave propagate in one direction. Okay. So let it propagate along, for example, just x direction. Okay. So with all of this simplification, so we know that this field it just becomes the polarization, okay, times a function that only depends on x and t, right? So this will be a lot simpler, okay? So this one is the polarization. It could be horizontal polarized, vertical polarized, circular polarized, or counterclockwise polarized, and so on and so forth, right? So there could be many different, but never mind, we only need to consider one component. And then for this component, we have the simple equation, right? For this evolution, okay? So we have this wave equation for xt. That's a lot simpler, okay? So it can be written as partial square, partial x square, and per psi minus 1 over c squared, partial squared, partial over partial t squared, and the per psi, okay, equals to 0. Okay, so that is the wave equation for the electromagnetic waves, simplified to the simple case that we consider only one polarization for the electric field and propagating along one direction, x direction. Okay. And sometimes we, for your purpose, let me, in case you're not familiar with this, this is the notations. So you know that this square per se actually means you do this twice. So you do one differential with respect to x, and then do this one again. Okay. So it can be also written as partial x squared per se. Okay. And similarly, partial square over partial t squared per se. That actually means partial over partial t and partial t. So you do a differential of this wave function with respect to t once. After that, you do this again. Okay. So this one can be also written as partial t squared. So are you familiar with this kind of things? I suppose you are just starting to learn this partial differential equations, right? So this one is called PDE. Sorry, this color is not the best. Let me change the color to be, wow. Okay, so this is called a partial differential equation. Okay, PDE. Suppose you are not familiar with this one. Okay, so I explain a little bit the meaning of these notations. Okay, and sometimes we also use shorthand notation. Sometimes we are a little bit lazy. Okay, right. So we just write a partial with a subscript x as to have the same meaning as this one. And similarly, partial x squared, that actually means partial squared, partial x squared. Of course, you know that we can also call this partial y, partial z, right? Okay. Okay, and let's look at the solution of this. So guess what's the solution of these waves? You already know that what's the solution of Maxwell equations in a vacuum, right? The solution is simply just plane waves. Okay, let me just write down the okay. We call this one cosine k omega x and t. Okay, so because it's given by this k and omega two component and depends on the x and t. Okay, And this K has the meaning of wave factor. And this omega means it's called angular frequency. Okay. Later we're going to see that there are two are not actually independent. So if you know K and then you know omega, okay. So to check this one, let's do the practice of calculation, okay. Let's check. Let's look at the partial t, eikx minus I omega t. So this is a differential with respect to t of this exponential function. So the result is just minus I omega eikx minus I omega t, right? So it does not change this wave function except for just a constant. So in this sense, we say that this one just give this factor. And if you do this twice, you know that we just apply this differential, this expansion function once again, right? So that give you another factor. So that will give you this one. Right. And then similarly, you can apply this one to x. That of course will give you ik e to ikx minus I omega t, right? Very simple. And if you do this twice, okay, so that will give you twice, right? Another one. So you put these two together, do the difference. You can see that the result actually is you have a partial square, partial x square per psi minus partial square, partial t square per psi. That's c square, right? Sorry, let me. So this one actually equals to ik squared minus 1 over c squared minus I omega squared, right? And the per psi k omega. That should be 0, right? Okay. So let me copy this. So you have, so we have obtained this one. So the only possibility that you must have okay, so this means you have omega square equals to c square k square, right? So this is the solution. So that means the solution, as long as you have this so-called dispersion relation. Okay, so if this one is correct, then you have the wave equation is satisfied, right? Okay. So this is the solution of this one. And this one is called a dispersion relation, okay? And of course, we also often write this one as omega equals to C and the modulus of K. So because we call this one and the angular frequency, and this one should be positive, right? And this is non-negative. Okay, you can choose this one to be non-negative. Okay, so this is the one thing. Okay, and also the solution. We have two indices, K and omega, but we only need one because omega is determined by this one. So we can write down this one as simply e to I kx minus omega t. Okay, so this one actually can be also written as I k x minus ct, something like this one. Okay, so if we just assume k is positive, okay. If k is negative, and then just change the direction. Okay. All right. So that is the solution. So, of course, you know there's another way to do this. Okay. And you can also use if you assume this field should be real, right? So that means you have two components. You can use the cosine kx minus omega t, or sine kx minus omega t. Okay. So in general, if we give wave factor the general solution, it can be written as a times cosine kx minus omega t, and plus b times sine kx minus omega t, right? So you have two variables. You have two free parameters, okay, to form a general solution, okay. But you can also use another way to do this one. So this one can be also written as, say, a constant times cosine kx minus omega t, and plus a phase, right? So this is a way to do this. So you have still two free parameters, a and phi, right? But you can also write down this as a constant e to I kx minus I omega t, and then you take the real part of this one, and now you have similarly you have only one parameter, c. But remember, this c is a complex number. Okay. So that means you still have two free parameters, right? Real parameters to give a general solution. Okay. Okay. So that means you have this one is the general solution. Okay. So any solution can be written as a combination of this one. So this is we already solved this equation, and with this. Right. So let me summarize. So the equation, sorry. So the equation is partial x squared minus 1 over c squared partial t squared and per se xt equal to 0. So the general solution is c per se k omega that equals to c e I k x minus I omega t. For one, this is only for one wave factor. Okay. But in general cases, we can have many solutions. And remember, this equation is linear. PDE. What means linear? Linear because this PHYS xt shows only once, right? So you can see, that if you have if PHYS say is a solution, and then you can have any constant time system is also a solution, right? That's very easy to check because you can add a constant. So if you add a constant c right here, okay, so this one just is equivalent to c partial x squared minus 1 over c squared partial t squared plus psi equal to 0, right? So this is one property of this linear. So another one is secondly, so if you have two solutions, PHYS 1 and PHYS 2 are solutions. So you can see that you have this. And then you look at any combination, complex number C1 times PHYS 1 and the complex number times C2 PHYS 2. So this one will equals to, because this is linear, so you can separate it separately. And then you know that this is a solution, so this one is also a solution. This is a solution, so this one is also a solution. So that means this one equal to 0 and this one equal to 0. So the summation, to add these two together, so this still give you 0, right? So C1 PHYS 1 plus C2 PHYS 2 is also a solution. So this is a nice property of this linear PDE. So that means if you solve one solution, okay, you can multiply constant, got another solution. If we have two solutions, you can combine them, okay, to have more solutions, okay. So this one is called a superposition. That means you combine them of PHYS 1 and PHYS 2, okay? It's a linear combination. Okay. So now we got some interesting result, right? We know that PHYS k equals to EIK x minus I omega t is a solution. So you can have any k. So this is a set of solutions. Right. So that means you can write any function as a summation of this k with coefficient PHYS k, okay? EIK x minus I omega t. They should also be a solution, right? So that means anything of this one, any linear combination of these plane waves, okay, is also a solution. And this one is called a wave packet. Okay, so we're going to understand a little bit more meaning of this name. Okay, why this one is called a wave packet. Okay. So actually, any function psi xt can be written as okay. And also we know that in particular, this one can be written as an integration form, okay? So we write this one, xt, that equals to integration. And now we use a function psi k, tilde k. Do the integration over k. Sometimes we use a convention, okay? Just put 1 over square root of 2 pi right here, okay? Right. Some of you already recognize this one is nothing but just it's just the Fourier transform. Why? So if you take a t equals 0, say if you take a t equals 0, so you find that any function of x can be actually written as the integration of a function of k times this plane wave. Right, so this is it's called the Fourier transform. Okay. And then by the Fourier transform theory, we know that you have the inverse. So actually this psi tilde k will just equals to psi x e to minus I kx and then dx, okay? So this one is called the inverse Fourier transform. But I don't like this name of inverse, okay? So I put a double quotation right here because it doesn't make any difference. So you can call this one Fourier transform, another one inverse, okay? So usually for me, I often just abuse the, you know, to abuse terminology. Both called the Fourier transform. Okay, so we don't distinguish the Fourier transform, the inverse transform, unless there's really confusion there. Okay, otherwise we just call all of them Fourier transform. Okay, to save the to make them equal. Okay, right. Okay, let's see some examples. Okay. Right. By the way, from this one you can see that this immediately solves the initial problem, initial value problem. Okay. Okay. Suppose at t equal to 0, you know the wave function is like this one, and then we, by Fourier transform or inverse Fourier transform, if you like, you know that the psi tilde k can be written as 1 over square root of 2 pi, and you do the integration. Okay, this integration, if I don't write down, it always means the integration from minus infinite to plus infinite. Okay, you obtain this one, and then you know that the psi k x can be written as 1 over square root of 2 pi percent tiered k. Just copy this one, right? EIKX and dk. And then you know that the EIKX just equals to EIKX minus omega t at t equals 0, right? So that means this is nothing but just the solution of the plane wave solution at t equals 0. So then simply you just put this time dependence phase factor back into the solution. So you got the percent xt, the time dependence, we are simply equal to 1 over square root of 2 pi percent tiered EIKX minus I omega t. That solves the problem, right? Sorry. Okay. So this is a solution of initial value problem by Fourier transform, or by the expansion and of the initial state into different solutions. Okay. Right. For example, let's say we have a solution like this one. Let me try to keep the notation the same as we have in the, okay. Okay, and this sigma is just a constant. What is this form? So you can, this is a Gaussian function, right? So it's a Gaussian function. And the Gaussian function is a very nice function. So we're going to get more familiar with this one. Okay, so this is a very lovely function. Okay, I like this one very much. So let me show you how it looks like. It's a beautiful shape. Okay, as a function of x, and this is 0. So you can see, first of all, it has maximum at this 0. And then decays to 0 for large x. But it's x squared, so it also is an even function. Okay. You know, my drawing is not as beautiful as it should look like. Okay. And this width is about 2 sigma. So you can see that. And this is the maximum value, right? So sorry, 2 sigma to the power minus 1. Also. So when x change to 1 over sigma, okay. So this one will decay to about e to minus 1/2, right? And this one will be minus 1 over sigma. Okay. So that is a very nice function, okay? So we're going to see a lot of beautiful properties of this function later, okay? But let's try to do the Fourier transform of this. Let's calculate the Fourier transform. We wish to see how this wave packet, suppose you have this wave packet in the beginning, how this one would change at a later time, right? Okay. According to our definition of this one, so this should equals to percent x e to minus I kx and d x, right? So basically, we're going to do an integration something like this one. Okay, from minus infinity to the plus infinity. And this integration actually is can be transferred into another simple integration. So let me first show you how to do this kind of a Gaussian integration first, okay? Let's do the Gaussian integration before we do that Fourier transform, okay? So this is something probably you have already known, but I want to emphasize this to you because this is probably the only important integration in physics, okay? How do we do this integration? So this is equal to what? Let me call this one I. Or maybe call this one G, Gauss, okay? So G equal to what? Have you learned this one before? Okay? Have you learned this one before? Okay? It doesn't matter, okay? So we're going to do this calculation. And this one, there's a trick to do this one. G squared, of course, equals to e to minus x squared over 2 dx squared, right? That, of course, equals to that's very simple, right? We just do this twice. By doing twice, actually, it's easier than doing once, okay? Because we have a trick right here. Sorry. We change this variable to be y. It doesn't matter, right? Because it's dummy. So you do the integration of x and do the integration of y, that's the same, right? And now then I can change this into a two-dimensional integration. Okay. Doing integration in two-dimensional seems to be more difficult than doing integration in one-dimensional, right? But this is not actually true in this case. So we can change the variable x, y to the polar coordinates rho and phi. Okay, so that you know, right? So this is x, y, and then you call this one angle phi. This length rho. Okay. So then you have this square will equals to e to minus x squared plus y squared, just rho squared over 2, right? And dx dy will become just rho d rho and d phi. And now this function does not depend on phi, so that will equals to 2 pi, the integration over the angle. And this one will be the rho change from 0 to infinite. That will be rho squared. But rho d rho just over 2 is nothing but just rho squared over 2, right? And what's left, you can see that this is nothing but just that's 2 pi, right? Okay, so we solved the problem. So g squared just equals to 2 pi. So that means this one just square root of 2 pi. Okay? And now with this one we can calculate this integration, this Fourier transform, more easily. Okay, so now you can see that psi tilde k equals to 1 over square root of 2 pi times sigma over square root of 2 pi and the integration e the minus ikx, and the plus sigma square, minus. And dx. So this is not exactly the same form as we have known for the Gaussian integration, okay? Because there's a linear term, but we know that any linear term can be combined into the square terms, right? So that equals to square root of 2 pi, 1 over square root of 2 pi, sigma over square root of 2 pi. And now I can do this one, change this one to be sigma squared x squared over 2 plus 2ikx. What I need to do is just to simply minus k squared over sigma squared. So that will make a perfect square. And then you should minus k squared sigma squared over 2. And then dx. Okay? So now this one is a perfect square. It's 1 over square root of 2 pi times sigma. And the integration e to minus. What's inside is going to be a perfect square. And then you have another function that does not depend on x. And then you do the integration of x. But now you can times sigma right here and divide the sigma right here. And the integration is infinite, so you can plus any constant to here, does not change the value, right? But this part, this part, and this one, it's nothing but just this Gaussian integration. So that equals to square root of 2 pi. Okay, so this one just equals to something like this one. So that is square root of 2 pi, right? So the final result is beautifully it's still a Gaussian function. Well, so this gives us a very beautiful result. So let me write down this result. So if percent x equals to and then percent tiered by Fourier transform. So this is so beautiful, right? So the Gaussian wave packet, the Fourier transform of Gaussian wave packet is still a Gaussian wave packet. You can transfer this back. This is the inverse Fourier transform. So you can see that this is, sorry, I made a typo right here. Should be minus 2 sigma k squared, okay? Right. So this is just the inverse to each other, okay? And to check this one, because sigma, the dimension of sigma is equals to the dimension of k, equals to the dimension of 1 of x, right? Okay. So that's a dimension analysis, so that you know that this cannot be wrong, right? So this is the beautiful property of the Gaussian function, okay? If you have a Gaussian wave packet, you do the Fourier transform, and then the result is still this one. So in other words, you say that this, and then the solution psi xt will be simply okay. So the question is, this one equal to what? Okay. Let's take a break and we're going to show how this Gaussian wave packet propagate in the space. Okay. So if you have questions, you're welcome to ask. And look, can you see this screen? Can you see this screen?
The blackboard.
So we define psi k tiered equals to 1 over square root of 2 pi, right? That's the derivation. We call this one Fourier transform. Okay. Sometimes we don't have this factor, for example. So this is another way to do this. Okay. And then let's check this psi x. And we know that there should be a factor right here, but this factor is what? We don't know. Okay. Let me put 1 over something right here. Okay. Or maybe I just don't use any factor right here at this moment and see what will happen. Suppose I don't add any factor.
The thing that I do is just multiply the frequency spectrum.
And then this will be psi tiered k e I k x and d k, right? But let me put this into this one. Insert this one. So this one will equals to ek e I k x e the minus I k y and psi y, right? And dy. So this is something that we're going to have. And this will equal to e I k x minus y and psi y dk first and then dy. Okay. And then what is this one? What is this integration? So the question is, so this is something that we haven't learned yet. Okay. Okay, so this one, if some of you may know or not, we call this one a delta function x minus y. There's a 2 pi right here, okay? So that's a little bit more advanced. There's a appendix in the lecture notes introduces this delta function. So I don't have time to cover this delta function at this one. So because of this delta function, delta has a nice property. So what's the meaning of this delta function? It's a function like this one. It's a very sharp function. So this is delta x. That equals to 0 everywhere, infinite at x equals 0. Okay, and also has the area of this one is always 1. Sorry. Okay. So now then, if you have this one,
after your modulation on your equivalent to this is
if you have this one, and you know that if you have a function, for example, delta x dx, because this function is basically you have a function, this is fx, and this is delta x. So the multiplication of this one will be just simply equals to
why I have to choose an initial phase.
So fx times delta x will just equals to f0 times delta x, right? Because delta x is 0 everywhere. So the integration of this one, we just use the integration of this one. But f0 is a constant. So that will just equal to f0. Right. So that means this delta function basically just a sampling. Okay. Okay. So then this one can be written as 2 pi times the delta function x minus y per psi y dy. Okay. Now you look at that. This is per psi y, for example, and this is the delta function delta x minus y. So it's 0 everywhere, but only at this x equal to y at this point, it's not 0. So that means this one will give you a sampling of this function. That's y equal to x, right? So that means this result will be 2 pi times per psi y, sorry, per psi x, because the integration is over y. But then you have a problem. This is not equal to this one, right? So if you divide this by 2 pi, this divided by 2 pi, this will divide by 2 pi, this will divide by 2 pi, and this will be cancelled. That equals just 2 per psi x. So that makes this everything to be consistent. Okay. So the reason of this one is because of the integration of this one has a 2 pi in this one. So you need to guarantee that this delta function has the area, to be 1. That's the reason of this 2 pi. Okay. So suppose you don't use 1 over. You can use if you use 1 over square root of 2 pi, and then here of course you don't need to divide by square root 2 pi, right? This you can do this one. Okay, and then the result is still the same, right? So there's a 2 pi factor right here. So you have to divide this one either in the Fourier transform or in the inverse Fourier transform, either equally or just on one side or another side. So there are different conventions. So I'm using this convention that the Fourier transform, the inverse Fourier transform, they have a symmetric form equally, right? So I want to have a Fourier transform and the inverse Fourier transform are just the same. Okay, they are not much different. Okay. All right. So I will save this slide also. But I don't know if I have time or not. If I have time, maybe at a certain point I can give you a more systematic introduction of this delta function. But we don't need this one, okay? So even though a lot of discussion, mathematical discussion, will be a lot of convenient by using this delta function. But it's, at the beginning, it's slightly abstract. But it's elegant. It's very elegant and a very useful way to do it. Okay. Otherwise, it's going to be clumsy. So we're going to come back to this one point maybe later. Okay. So I hope that one not confuse you with this square root of 2 pi. Okay. But never mind. You just say that you have to have this square root of 2 pi factor to make sure that the result is consistent. Let me see any other questions. Yes, Chokmin gave an excellent answer. It's for the convention to make the Fourier transform and the inverse Fourier transform to be symmetrical. That's right, perfectly. Okay, can you see the screen at this moment?
Yes.
Great. So we have seen that if you have a Gaussian wave packet, like this one, that is okay. This is a Gaussian wave packet with the weights to be 2 over sigma, like this one. And then by Fourier transform, you actually got another wave packet. That's also Gaussian. Okay. But now the parameters is slightly changed. Of course, you can transfer this back by another Fourier transfer or the inverse Fourier transfer if you want. That's what we have done, okay? Before we proceed, let's summarize a little bit of these features. So what's the width of this one? What's the width of this? So this one is actually 2 sigma, right? So you can see that if the width of the real space wave packet increase, and then the width in the K space, the wave vector space, will decrease, right? So that means if you make this one to be, if we make this one shrink, so if we shrink this one to this one, for example, and then this one actually will be broader. Right. So if you do this change, or if you make this one to be wider, you can have this one to be narrow. Okay. So a broader feature, a broader wave packet in real space will give you a narrow wave packet in the K space. Okay. So if we call this one delta Kx, and this one is delta K, it's a kind of inverse proportion to this one, right? Or in other words, we say that this delta Kx, delta K is kind of like a constant. Right, so if we have a wave packet better defined in a real space, it's going to be worse defined in the K space and vice versa. And this feature later on, we're going to show that it's closely related to the uncertainty relation in quantum mechanics. Okay, but let's just know this one, and then let's come back to this propagation. How would this one propagate? It's actually very simple because of this linear dispersion relation. Okay, let me show you. So now we have PHYS x just equals to this Gaussian wave packet, right? And do the inverse Fourier transformation. Okay. And we want to have the time dependent. So what we need to do is to minus I omega t right here. Okay, that's all we need to do. But remember, omega just equals to c times k, right? This is the dispersion relation. So why we call this one dispersion? It will be later, will be clear, okay? So you just need to put this back into that one. So there will be 1 over square root of 2 pi, 1 over square root of 2 pi sigma, okay? E minus K square over 2 sigma square plus I K X minus CT and dk. So now you just by staring a little bit, you can see that what you have done is nothing but just change it. You have done is only the change that x change to x prime equals to x minus ct, right? So that means the result is simply you just change this x to x prime, that equals to psi x minus ct. Mathematically, we know that this is actually very simple. So this is psi x, that's the initial state. And then after some time, this one will be just displaced to that x equals to ct, to a new position. Okay, so this is just psi x minus ct, right? So this one is the propagation. Okay, so basically you just have the propagation of the wave packet from x equals 0 to x equals to ct. So this velocity is called a group velocity because this is like a group. Vg just equals to c. Okay. And this one is nice. It's true actually for all kinds of wave packet. So we have considered this one to be, you can see that in this derivation, we haven't used any specific property of the Gaussian. Okay. So for any wave packet, not necessary Gaussian, okay. Anyone. So you know that psi xt equals to 1 over square root of 2 pi psi tilde k eik x. But now you just need to put minus I omega t right here, dk, right? And then this one replaced with that one, so that equals to 1 over square root of 2 pi psi tilde k e to I k x minus ct dk. So that just equals to psi x minus ct. So it's just a translation, okay? Right? So in this case, let me summarize for light with the important thing is omega equals to ck. So that's the fact that we have used in that derivation, right? So we have, if we have x at t equals 0, and they're going to have psi x minus ct at t. Okay, so it is first of all propagation with group velocity that equals to c. And secondly, there's no change of shape, no distortion. That means no distortion and no dispersion. Okay. So this is the case, but later on we're going to see that this is not always true. That if we in general, if this one is not equal to c times k, okay. So this is if we don't have this c times k, actually not necessarily the wave packet will keep the same shape. Okay, but we come back to this one a little bit later. Okay. Before that, let's do another example for Fourier transform. Okay. So we consider the square wave. Okay, that equals to 0 if x is greater than a over 2. As 1 if x is less equal to a over 2, the absolute value. Okay, so this is minus a over 2, this is a over 2, this is 0. Okay. So this is another thing that we want to have. Okay. Right. And this Fourier transform is very simple. It's extremely simple, right? Let's just do this one. Per psi tilde k that equals 1 over square root of 2 pi, right? The factor that you have been worried about a little bit. Minus I k x from minus infinity to the plus infinity times per psi x dx. But because this is a square function, so the integration is simply just from minus a over 2 e to I kx and dk over square root of 2 pi, right? So minus. And this one, of course, have an imaginary part and a real part. This solution is it's very simple. It's minus ik times over square root of 2 pi, and then you have e the minus ik a over 2 minus e the ik over 2, right? And this one is nothing but just a sine function ka over 2 divided by k over 2, right? Times square root of 2 pi. Okay. So that result is nothing but just square root of 2 pi times k a over 2 pi times a times sine ka over 2. Mathematically, there's a function called this one a sinc function. Okay. And this sinc function has a feature, okay? So a nice feature. So if we have a square form by a Fourier transform, it's going to be the sinc function. The sinc function is so that equals to a times sine k a, therefore ka over 2. So you can say that if k is 0, so this one is just 1, right? So this one is just 1. And then if ka equals to 2 pi, so this is goes to 0. Okay? So this goes to 0. Okay? And then this will overshoot. But then as this ka over 2 is growing, so this one is going to decay, okay? But slowly. Sorry, very bad drawing, okay? But anyway, so you know that this decay is 1 over Ka, right? So it's basically it's K to power minus 1 decay. It's very slow decay. And again, the weight of this one is going to 1 over A, right? Roughly. And this one is A. So if you take this 1 over A as the weight of this wave packet, so you have a delta X. This, of course, is just A, right? And this delta K is in order of 1 over A. And again, you have this one increase, and this one will decrease. This is one feature, okay? And but here you have another feature. You see that there's a decay of this one. There's a long tail, unlike the Gaussian wave packet. There's also long tail. As 1 over K, okay. This is because here you have a very sharp feature right here. Because you have this square. At this point, you have partial f, partial x equals to infinite. Okay. So if you have a very sharp feature in the real space, and then you're going to have a long tail structures distribution of this wave packet in the K-space. The reason is also very simple. So remember, if we have Fourier transform, okay, you wish to have if I have just a cosine function like this one, right? So that gives you a very smooth one. And if you have if we add some fast oscillation, so that will give you, something like this one, right? So that will give you a little bit sharp structures. But if you add even more, if you have add more high frequency ones, and then you can slightly change this one to be even. It's better approximation of this square. And if you want more and more the waveform approach to this sharp structure, need the higher and high frequency ones. Okay, so that means whenever you have a sharp feature right here, you should have a long tail in the K space. Okay, so this is another feature of this Fourier transform. Okay, so this is an example. So let me summarize this feature of Fourier transform. So one thing of this one is so if I have a wider in real space, and this one is going to be narrow in K space. And secondly, the sharp features in the real space will give you longer tails in the K space. Right. So there are a lot of examples of this application. For example, if you do the grating, okay, you know that if you have a grating, and then the larger the grating is, the sharper the diffraction lines will be, right? So this is another way of this kind of conjugate relations between the real space and the K space. Okay. Right. So that is the two important things about this Fourier transform. Now let's talk about the more general waves. Okay. Suppose we have a more general omega k. Okay. And not just omega k equals to ck. Okay. And this one is something that we're going to encounter in quantum mechanics. We're going to see what if we have such kind of solutions. So we still have the solution, say, suppose kxt just equals to e the I kx minus I omega t. But now this omega is not just omega k. But this omega can be supposed to be can be written as omega 0 plus d omega over dk times omega, sorry. You can still do the expansion, right? Okay. All right. So do we suppose we have a wave packet? Okay, let's say suppose we have a wave packet initially. That's something we can do, right? So the question is, Okay. So we're going to see what we're going to do with this kind of things. Okay. Let's consider an example. For example, if you consider de Broglie waves, for example, you have h bar omega equals the square, that's energy square, right? Minus the momentum p square, c square. That equals to m square to the c to power fourth, right? Okay. So in that case, you're going to have omega minus h bar square, k square, c square equals to m square c to fourth, for example. This is the de Broglie wave, okay? This will give you a quite a complicated result of the dependence of frequency on the momentum, on the wave vector of this this matter wave. That will be m square c to power fourth plus k square c square. Of course, if m goes to 0, you can find that omega actually goes to c times k, right? But if m is not 0, if m is large, or if m goes to infinite, you find that this omega can be kind of expanded as m square c square and plus k square and h bar square. H bar, sorry. C square, therefore, let me see. There's no C square. It's something like this one, right? So you can see that at different limits, so you can have this dependence of omega on K could be different. For the massless case, you actually have this linear dispersion, just like light. But if this is massive, this dependency is mostly like a parabolic decay, right? So that's one example that you don't necessarily have the frequency, angular frequency depends on the K, just simple as this linear one, okay? But if at this one, then we're going to have the propagation of the wave packet. Suppose you initially have something like this one, okay? And then this, in general, you're going to have, so this is per se xt. So you can have a number of things to happen. First of all, moving. Secondly, there's something called broadening. They could also change of called a distortion. Okay, so the wave will be changed. The reason is like this one. So per se xt that equals to right. So you can see that in general, you know, so this one will cause some phase shift of different K component. Okay, so this one depends on K. So this factor will, of course, leads to minus I omega K T. That's a K dependent phase shift. And the K dependent phase shift actually is important. Okay, so that will change the different interference So let me show you why. Let's say suppose you have a function like this one, also a function like this one. Okay, then you add another wave. But the frequency is slightly different, so okay. So you can see that at this point is kind of in phase. So they have the same phase, right? But at this point they are out of phase. So this one will lead to, if we add these two together, this will give you constructive interference, and this one will be destructive. So then if you add these two together, actually you got something like this one. The oscillation of this one will be, at this point, they're going to be constructive, and then at another point, they're going to be destructive. So you're going to have something like this. Okay. So the interference between the two will make a shape of this one, right? But suppose now if you have a phase shift, if you add a phase shift, change this one to be something like this one. Okay. And then you're going to have different point of this. So this shape will be changed to another location. Right. So the phase shift will lead to the shift of the shape. Okay. Even more explicitly, let me give you the Gaussian case. Okay. For example, we know that if I have a Gaussian wave packet by Fourier transform, this one gives you a lot of components. That's right. Of course, this will transfer back. But now let's add a phase shift. That means we change the phase for different K component. So originally you should have this one, right? Okay. But what if we add a phase? We add a phase like this one. So if we transfer this one back, so what will be this result? Guess what will be the result? It's actually very simple. So because the wave packet will be percent tiered K, but now you have this new phase, right? So this is a phase shift, okay? That's the same thing we added, okay? We added this phase shift. And then you do the Fourier transform. And let me change it to the minus sign, okay? It doesn't matter, okay? But anyway, you add a phase shift like this one. And now this, you can see that you can combine these two. So that gives you percent tiered K, EIK, X minus X0, DK, right? So you can see that if you add a phase to different components, okay? And it's nothing but just you have, change the shape so that this one will becomes, it's almost the same as the original one. But now this is shifted by this X0. Okay. So the wave packet will be changed to, this is 0, this is x0. So it's shifted. So this gives us another interesting feature of this one. So the phase shift in K space, for example, that's E minus I K x0. So this one will lead to, a displacement in real space. So x will change to x minus x0. Okay. So per se x will change to per se x minus x0. Of course, if you do the same thing, you will have this one as well, right? Okay. So if you do the same thing for real space, for example, if you have this e to sigma square x square over 2, this is a wave packet. What if you add a phase shift k0 x? So what will be this one? Okay. And then by Fourier transform, you know that this one will be minus k square, right? This is what we originally obtained. But you know that if we do the calculation, you know that percent tilt k will be percent x e minus I kx dx, and this one will be e to sigma x squared over 2 plus I k0 x minus I kx. So you can see that now this one, what you have to do is just replace k to k minus k0. That will be sufficient. So that means what you need to do is just to change this one to this, right? So that means it's just a shift of this K space, okay? So that means if you originally have a wave packet like this, right now you add a kind of phase, make this one to be colorful. So you times e to I k0x. So that means the phase of this one will be different at different position, right? So this is only the phase change. So if we plot percent x module squared, actually is unchanged. Okay. So because this is only the phase shift. But in the K space, this is the original percent tilt k. But it will be changed to a new one. Percent tilt k minus k0, right? Okay. So basically, you have a phase shift in the real space. You can have a displacement in the K space. If you have phase shift in the K space, you have a displacement in the X space. Okay. So that is another interesting effects about this Fourier transform, about interference. Okay. All right. And then what will be the effects of this for the propagation? Okay. What will be the propagation? Let's look at the propagation of this one. Suppose you have, and then percent xt. Suppose you initially, that can be written as right. And to do this one, we know that you can write down this one as percent tilt k e to I kx Okay. Minus I omega t, right? And dk. And now this omega will introduce a kind of phase shift in the k space, right? So omega will lead to a phase shift. Depending on k. So that means that will change, because the interference of k of different phases, that will change the shape of this wave packet, make this one to move, right? But this one in general is very difficult. So we have seen a special case. If omega equals to ck, that was very simple. It's just k change to x minus ct, right? So that's just a simple displacement. But what if it's not? That could, in general, could be very difficult. Okay. So the question is, how do we find out this one? So the idea is that suppose you have a wave packet that has a very small distribution at this k0, okay? And then this omega then can be expanded by omega 0 plus k minus k0 and d omega dk at the k0 and plus k minus k0 squared and d omega over dk, second order k0, of course divided by 2 factorial, right? And so on and so forth. And then we found that omega 0 actually will give you the so-called phase velocity. And omega prime that equals to d omega dk will give you the group velocity. And omega prime prime that equals to d omega squared dk squared, that will give you the spreading of the wave packet. Okay, so they have different results of this one. Okay, so the reason is the derivation is actually like this. So you have percent tilde k that equals to, remember, is minus 2 sigma squared k squared. Okay, and shifted by, sorry, k0, right? So this is for the wave packet that we have for, and now for percent x equals to okay. So percent xt will equals to e to minus k minus k0 square over 2 sigma square. Because this sigma is square small, so we can, when you do this integration, so we can do the expansion so that we can perform this integration. Otherwise, it's difficult, right? Now the zeroth order is just omega 0 t. And they have the first order. And they have the second order. Okay, and do the integration, dk, right? Here we have to drop all the constants because they are not really important. Okay. And now you can see that this one actually can be combined with this one. Okay. This one is just a constant, can be moved outside. Okay. So what you can do is that this can be written as e to I k0 x minus omega 0 t. That's the constant term we can move outside. Now what's inside is e to minus k0 squared over 2 sigma squared, and minus I k x minus omega prime, sorry. So plus I k minus k0 and x minus omega prime t. And there's another term so you can change this integration to be k minus k0 because it's the integration over E bracket. But suppose you don't care about this second order term. You just look at this term. This term is exactly the same as we have done for the light wave, right? So that means this will give you a propagation at velocity okay. So that is something like this one. Okay. But how about this term? But if you do have this term, it's nothing but just you have you just change this one to be you have an extra term. So basically you are changing sigma square, change it to be sigma square plus omega prime square I omega prime times t. So that means you are making this broadening factor to be larger, okay? So that means in the real space, so this one will give you a, you know, we take the modulus of this one and then make this tends to be broad, okay? So it means that second order derivative actually will give you the spreading of this wave packet. And the first order will give you the group velocity. And the zeroth order will give you the phase velocity. And this phase velocity is just omega 0 divided by k0. Okay, so you can see that this is because if you at t equals 0, the phase is ik0 times x, right? But then after some time, the position at x equal to omega 0 divided by k0 will have the same phase. Okay, so that means this is the phase velocity. So then you can see that so if you have a dispersion like this one, for example, okay, suppose I have a pointer here. This is k equal to 0. This is k0, okay? And then this one, this curve is omega 0 divided by k0. That gives you the phase velocity. And if you have this one, the slope of this one, that's partial omega, partial k at k0. That gives you the group velocity, okay? So this one is something that you know, a particle will really move. For example, if you have omega equals to h bar square k square over 2m divided by h bar, and you know that the group velocity will equals to partial omega partial k, that equals to partial k over m. This is nothing but just the momentum over m, that equals to the velocity, right? So this one is always less than the light velocity. But this phase velocity, actually, that could be h bar omega over, sorry, the omega over k0. That's h bar omega over h bar k0. That equals to energy divided by this momentum. but momentum could be 0, and energy has a mass, so this one can go to infinite. Actually, it could be greater than the light velocity, right? But the important thing is that this group velocity is something that we really care. Okay, so the group velocity carries energy and information. Okay, the phase velocity actually is only how fast, but the phase, the absolute phase is not meaningful in the waves, because you can always add a global phase factor to the waves without changing its intensity, right? Okay, so that's something we have for this propagation of the wave. Okay. All right. So let's stop here today. So see if any of you have questions.